Hello and welcome to another lecture session on classical motion of a single particle. In this lecture, we simply continue our previous discussion on the motion of a single particle under an inverse square law of force. And also, to be very precise, here we will be mostly dealing with the attractive inverse square law of force, and this is because the main attractive inverse square law of force can be seen and we actually experience every day, and we can even claim that we live for that, that is the attraction force between two mass particles, that is the gravitational attraction. And if you just remember Newton's law of gravitation, this is simply nothing but an attractive inverse square law of force. Okay. So, now coming back to the analytical part. So, as I said in previous lectures, we have discussed several points actually already on inverse square law of force. So, first we said that again. So, this is a central force law. So, I can write generally an inverse square law by this expression minus k by r square times r cap, where k is a positive quantity, that gives me attractive inverse square law. And then the corresponding potential will be equal to minus k by r. So, the potential or the potential energy of will be a negative quantity, because k is positive and r is also positive. So, this is a negative quantity. Then I said that the total energy can be written now in this way, where we know of course that these two terms actually are coming from the kinetic energy term. This is coming from the radial part of the velocity and this is coming from the cross radial part of the velocity, and this is the true potential energy, and the sum of the two remains constant because this is a conservative force field. Now, this quantity and is called the effective kinetic energy, and this quantity together they are called the effective potential energy. Why this effective terms? Because if you write in this way, then it looks that the motion is effectively one dimension and the only space variable under consideration is r. Okay. Now, you can also write this in this way, that half m r dot square plus some v effective, you can call the sum as v effective. So, we already discussed how v effective behaves as a function of r, and we had a plot like this. And if you remember the nature of the plot, actually you will see there is a very interesting point to note, that under such a condition, if you somehow, so here you see for very small r, it starts from a very high value, then it decreases and being positive, okay, that is why v effective has a positive value for very small r, and then with increasing r it decreases and then it crosses r is v effective is equal to 0, and then it reaches some local minimum value, again it increases and finally it asymptotically touches the r from negative side. Okay. So, in a sense, if you now think the motion under such an effective potential, you will simply can classify this by saying this is such an potential well, the effective potential well is such that, or the potential energy structure is such that, if you give the system any energy which is slightly greater than 0, here for example here or here or here or just but anything positive, the total energy is, if it is positive, then always you see that the system will simply have one turning point and the other turning point is missing, that means it is at infinity. So, this is an unbounded motion. This is true for inverse square law of force, which is attractive in nature. And if you give the system anything negative, okay, which is even slightly less than 0 here or here and even here, okay, until this, okay, you will always have a bounded motion, because you will then see that always the particle will have two turning points. Okay. What happens exactly at 0? Since it is asymptotically approaching 0, then even at 0 we can think that the system is having only one turning point, thereby making the motion unbounded. Okay. So, if I write that for E greater than equal to 0, the motion is unbounded, and E less than 0, the motion is bounded. Okay. So, that we already can conclude from this graphical analysis, and that is the power of such analysis. Now, you know that whenever you have such an attractive inverse square law force, we have already using Binet equation, we showed that the orbit of such a particle, okay, would be given by a conic section, which is simply r is equal to p by 1 plus epsilon or E cos theta. Epsilon and E will be, I mean, somehow used indistinguishably in the course, sorry for that. So, this is known as the semi-lattice rectum. See, you just search on internet what they are, and I think most of you know from your coordinate geometry class in the high schools, and this is the eccentricity. Okay. And so, this is a distance, and this is positive because this is equal to this m h square by k, which is positive, and this is a quantity, this is a dimensionless quantity, this epsilon, this is an eccentricity, and this is given by this quantity m h square c by k. Okay. So, these two actually defines the nature of the conic section, okay. And so, we will actually discuss that whenever the conic section. So, maybe all of you know that in nature we have 4 commonly encountered conic sections as far as my knowledge is concerned. So, one is the ellipse, another is the parabola, the third one is the hyperbola, and the fourth one is a special case of ellipse, which is known as a circle. Okay. So, I mean, so broadly classifying, they will be of 3 kinds: elliptic, parabola and hyperbola. So, an elliptic orbit is basically giving you I mean a closed trajectory basically, and whereas a parabola and a hyperbola can be giving you the possibility of a open trajectory. Okay, because a hyperbola and a parabolic trajectory, they are not closed, that we know from our geometric knowledge. Okay. Now, you try to associate this knowledge to Bertrand's theorem. Bertrand's theorem already said that if you are dealing with an inverse square force law, any bounded motion will assertively give you a closed trajectory. That means that here for this, here we can easily use this knowledge by saying that if I have the total energy of the system to be positive or equal to 0, then I will have an unbounded motion and I cannot expect assertively a closed trajectory. Okay. So, my trajectory can be open as well, although I cannot always say that the trajectory can be open or closed, but again you can use your common sense just by thinking that if your motion is unbounded, then there is, by common sense, there is no possibility of a closed trajectory. Okay. On the other hand, if your motion is bounded, then your trajectory can be closed and open. So, if your motion is unbounded already, you can analyze and conclude that your motion is unbounded. For this, then only open trajectories are possible, and then you can already think that only possibilities can be parabolic orbits or hyperbolic orbits. Whereas, if you go to this case E less than 0, that is the total mechanical energy of the particle is negative, then basically you will have a bounded system. Now, here there is a possibility of open versus closed trajectory, and Bertrand's theorem said for inverse square law we do not have to think anything, we do not have to be anxious about the nature of the trajectory, it will be a closed one, and here we know this will be a closed conic section. So, it will be either ellipse or circle. So, I can now write from this point that if I have a positive or equal to 0 total energy, then I will have either parabolic or hyperbolic trajectory. Whereas, if we start from negative energy, I mean if we deal with negative energy, negative total mechanical energy, then it will be either ellipse or simply circle, and actually you can say in general it is an ellipse. Okay. So, you see already just by doing this much of analysis we can conclude about the one-to-one correspondence to the nature of energy, whether it is positive or negative, the total mechanical energy and the nature of the orbit. Okay. Here we will somehow proceed in the same direction much more formally, and we will see that how the features of the conic section, that means the semilatus rectum and the eccentricity, are really associated with the dynamical variables of the system. For that, what we will simply do, we will just start with this solution, and you can say that okay, this theta 0 can be taken to be 0. So, this will be my solution. U is nothing but 1 over r. Okay. So, I am writing in case you want a recapitulation, U is nothing but 1 over r. So, I can now, so U is equal to, I know, k by mh square plus c cos theta, where c was a constant. Okay. And then I can easily write du d theta is equal to, so this is a constant quantity, this is a function of theta. So, c minus c sin theta. Okay. And now we again write the whole energy conservation. Now, the energy conservation gives half m r dot square plus L square by 2 m r square minus k by r is equal to E for an inverse square law, for an inverse square law, of course attractive for our case. For an inverse square force, I write like that. Okay. Then if I can write this, I also know that, I know r dot is equal to minus L by m du d theta. How would I know that? This is pretty easy to understand. R dot is dr dt. So, this is r dot, and this is nothing but dr d theta dt. So, this is a mathematical manipulation you have to use everywhere in the central force, and then this d theta dt is theta dot, and then dr d theta is nothing but dd theta of 1 over u, and then this part becomes minus 1 over u square du d theta times theta dot, and theta dot is nothing but L by m r square or h by r square, is, as you know, and from that I can actually rub this bracket off. Yeah, okay. And you can actually have, so r square and u square, they just make 1. So, it will be minus L by m du d theta, which is exactly what you have over here. Okay. If you know that, then simply you can write the total conservation of energy is equal to half m L square by m square du d theta whole square. You can also write plus L square by 2 m. Now, r square you can write as 1 over u square. So, it will be here, and then you can write minus k by r as minus k u, and that is your constant energy. Okay. And from that what you get is a fantastic relation that is almost like Binet type of equation, but for the conservation of energy. You can write du d theta whole square plus u square is equal to 2 m by L square E minus V, okay, where we know that V is nothing but minus Ku or K by R, okay, that we have said minus K by R. Okay. So, this is the expression which we will use now, and so what we will do, that we will simply put our solution u is equal to this and du d theta is equal to this in this one. And that is why you will finally see that finally we will have something very interesting. So, du d theta whole square will be c square sin square theta. Okay. So, I write c square sin square theta. Again, u square will be this whole thing whole square. So, it will be k by m h square plus c cos theta whole square is equal to 2m by L square E minus V. Clear? So, if you see, this is the final this is the expression what you have, then you can do a little bit of more simplification and you can come c square plus, just using that sin square theta plus cos square theta is equal to 1, you will have k square by m square h to the 4 plus 2 kc cos theta by m h square. Okay. And on the other hand, you write simply this is equal to, so if you just see E minus V. Okay. So, V is again, just you remember, I just write 2m by L square, E minus V is Ku, so it will be E plus Ku, and again instead of U, you just write this value, and then you will have 2E by mh square plus 2k square m square h to the 4 plus, yes, I have to multiply everything, just a minute, yes, by everything like this, yeah, plus 2kc cos theta by mh square. You see here again, instead of u, you wrote this expression, and throughout this whole expression you have used L is equal to m times h. Okay. So, I have got rid of L and I have written throughout the h. Okay. So, this is h to the, sorry, this is h to the 4. Yeah, h to the 4. Okay. Now, you see what is the good news, that this term will cancel and finally, you have something like this. So, c square, this is also another term there will be. So, this minus this will simply give you k square, this minus this will give you k square by m square h square. So, that will simply give you c square is equal to 2e by mh square plus k square by m square h to the 4. Okay. Now, if you remember what was that c square. So, from Binet equation we had this c mh square times c by k is equal to e. So, mh square c by k is equal to e mh square c by k. We know, we have. Okay. We have this already, and then I can simply write, okay, so C will be, then I can simply write that, or I can write this, I can do in both ways actually. I can go over here with a different color. We have already this. So, E will be is equal to m h square by k. Now, c will be root over this with a plus minus, I am just taking the plus sign over here. So, root over 2e by m h square plus k square by m square h to the 4. I have taken the plus sign only because from my this expression, you see, yeah, from this expression I have said that this will be a ratio which is in general positive, okay, and I will just take the plus over here. So, this will be the relation between the energy, the angular momentum per unit mass, the force constant and the eccentricity, and that is quite important. Okay. Now, if you just take this relation a little bit more carefully, you will see that E is equal to, simply if you just now insert, put this thing under the square root, you will have root 1 plus, so it will go inside being an m square h to the 4 by k square, which will totally be 1 over this term, and that is why you will have a 1 plus, so you will have 2 e by m h square times m square h to the 4 by k square. Okay. And you have the very fundamental result 1 plus 2 e m h square by k square. So, you see now that is the expression you already have encountered elsewhere. In the last lecture, at the end of the last lecture, I said that 1 plus 2 e L square by m k square, that must be greater than or equal to 0, and that is because that and since that is greater than or equal to 0, I can call it as the square of some some variable e or some quantity e. Okay, it is not a variable, sorry, some quantity e. And if you now think what they are, so in terms of L and m, this is simply is equal to 1 plus 2 e L square by m k square. Okay. So, you see this e is equal to this one, okay, and this e is nothing but the eccentricity. Okay. And this is totally inconsistent with this result that your E plus this quantity must be greater than or equal to 0. Okay. So, in that way you are also cross checking the consistencies of this result. So, now finally you have found that E, which came as the square root of 1 plus 2 e L square by m square, is nothing but the eccentricity of the conic section. Okay. In the next lecture, depending on the nature of the conic section, we will actually try to differentiate different type of conic sections and analyze the corresponding motion. Okay. Thank you.